All right, here's our video on quasars versus black holes. And here's something to know about that. Every quasar has a black hole in it, but not every black hole is a quasar. So think about that for a minute. So again, quasars have black holes. And in our galaxy, the Milky Way, we have a supermassive black hole, and it's called Sagittarius A. I'll write it over here. Sagittarius A. And it is a supermassive black hole in the center of our solar system. It's 26,000 light years from us. So we're pretty safe. 26,000 light years. Think about 26,000 light years. If you want to think about it in miles, it's about 150 quadrillion. Quadrillion. It's enormous. Sagittarius A. And at one point, Sagittarius A may have been a quasar. Quasars do not last too long when we're comparing them with other stars. Stars can last billions of years, quasars can last millions. And by the way, in our galaxy, we just don't have one black hole. We have one black hole in the center, Sagittarius A, but and think about this, we have at least 100 million small black holes in our galaxy. And again, we don't have to fear, but our closest one is called Gaia BH1. So I'll write that over here. Gaia BH1. And Gaia BH1 is about 1,600 light years away. Again, a light year is how far light will travel in a year, and light will travel about 6 trillion miles in a year. Not exactly, but about 6 trillion miles. Going 186,000 miles per second. So light is fast. Nothing is faster than light. And if you want to put that to miles, how far Gaia is about 9, but about 9 quadrillion miles away. A small black hole. Okay, so let's start with black holes. What is a black hole anyway? So let's clear this out. Let's get a clean page. And we'll stick with yellow. Why not? Stick with yellow. So a black hole is a collapsed star, a very massive star that collapsed. So our sun is way too small to become a black hole. So let's just write this here. A black hole is a point in space. Well, actually, not really a point in space. Well, we'll just write down a point in space where gravity is so intense. Let's just say strong. Gravity is so strong that nothing, no matter, no light, nothing, I'll put this no matter, no light, can escape. And like I said, it's a collapsed star. And to become a black hole, the star needs to be at least 3 times the mass of our sun after it goes supernova. So black holes will be stars that have gone supernova. Let's put a line here. A star has to be at least 3 times the mass of our sun after it goes supernova. So that means it must have been way massive before it, right? So our closest that may go supernova in the future is Betelgeuse. Some people say Beetlejuice, so Betelgeuse or Beetlejuice, whatever you prefer. So Betelgeuse right now is about 10 times the mass of our sun. And Betelgeuse is a supermassive red giant. It's a red supergiant that extends all the way. If it was in our solar system, we would extend all the way to the orbit of Mars. Let's get a picture of Betelgeuse. So if you go outside at night in the winter sky, you'll see Orion's belt right over here. Very easy to see in the southern sky. And then if you look up to the left, you'll see this kind of reddish yellow star. It's not really red, but you'll know Betelgeuse. And it's about 643 light years away. Very massive. Now, if it does go supernova, and we don't know when, but if it does go supernova, let's say it went supernova today, we wouldn't know about it for another 643 years because light's going to travel toward us. And if it did explode in our night sky, if we looked up at the night sky today and you see this gigantic explosion, because Betelgeuse will probably make our night sky very bright for a while. But if it did, then we know it happened 643 light years away. Right, 643 years ago, that is. And in, if you want to know in miles, it's about 3.5 quadrillion miles away. So Betelgeuse or Betelgeuse at one point will explode and become a supernova. And when it turns into its core, if that core is 3 times the mass of the sun, then it could become either a neutron star or a black hole. So like I said before, a black hole is a collapsed star. Like in the future, maybe Betelgeuse will become a supernova, then collapse. And the gravity is so strong. The gravity is so strong. We'll put this, the gravity, like I said before, the gravity is so strong that nothing escapes. Nothing escapes. No light is escaping. So if we do a two-dimensional image here, it's a 2D model, let's make our circle. Try to make a good circle anyway. And let's say that this is a two-dimensional model of a black hole. And this point in the center will be called the singularity. And around the black hole, they call it the event horizon. The event horizon. The event horizon is the point of no return. So anything that gets into the event horizon, that crosses the event horizon, will not be able to get out. And so if I change the color here and I show gravity is pushing inside this black hole, enormous amount of pressure, it's going to the singularity. So gravity is pressing from all directions into this singularity. If you cross that event horizon, you're not getting out. So if you want to think about, is it a sphere? Well, it's a collapsed star, so it's a sphere. And it's not really a hole in space, but you can say it's more of a gravity well. And every planet, every star, every object in the solar system will create a gravity well, which is a bending of space-time. So let's get a picture of that. So here we have the sun making its gravity well. See, it makes a gravity well, and the Earth has a gravity well, and Mars has a gravity well, and anything has a gravity well. And you can see it's almost like one of those games you put in the penny and the penny circles around. You may have seen them at arcades. But that's basically what's happening here. This is how we explain gravity, by this gravity well. So the sun has a much, much bigger gravity well than the Earth. A neutron star would have much more of a gravity well than the sun, and a black hole's gravity well will be almost infinite. So here we can see the gravity well that a black hole had. And if you get to the event horizon, get our pen going again. Here's the event horizon. Remember, if you cross that event horizon, you're not getting out. And that gravity well will go down to the singularity, and that could be, and some scientists say it's an infinite, which is hard to grasp. And going over here, you see a 2D representation where you have the event horizon. Don't cross the event horizon. And here's another picture of these gravity wells. We have our sun, a neutron star, and then a black hole. And the gravity is so immense in the neutron star, it's nothing but neutrons. But with a black hole, the neutrons have the gravity has basically won out, and it has collapsed that star completely, and you get this infinite hole or gravity well. So now we should turn to quasars. What is a quasar? Well, like we said previously, a quasar has a black hole in it. And quasars are extremely bright, or should we say luminous, right? Use a bigger term, luminous. They're extremely bright. They're the brightest objects out there in the universe. And when they first discovered them in 1963, they didn't really know what they were. This mystery out there in space. Let's get a little picture of that. And again, this is just an artist's rendition of a quasar. You can see these jets streaming out light years from the top and the bottom. So let's get our pen ready. Let's keep yellow. Why not? So what quasars are, and it's short for quasi, meaning somewhat or maybe, quasi-stellar, meaning star, because I didn't know what these things were, radio source. And they thought they were shooting out radio waves, which they are, but they're also shooting out X-rays. So they're shooting out X-rays. They're shooting out radio waves. Of course, X-rays and radio waves are all part of the electromagnetic spectrum. So they're shooting out all radiation from the electromagnetic spectrum. And how are they doing this? Well, you say, well, if there's a black hole, let's make the black hole green. If there's a black hole, how could anything be shooting out? So what quasars basically are, they're just supermassive black holes that are feeding on gas. Super massive black holes like Sagittarius A that are feeding, having dinner on gas. Gas that's surrounding them. So over time, of course, that gas disappears, and the only thing they will feed upon is anything that happens to cross the event horizon. So let's talk about this gas. This gas is being pressurized so intensely, incredibly intense, around the black hole, and the gas is going to heat up. So I'll write the gas around it. The gas heats up to millions of degrees, right? So it's like a pressure cooker. This heat is getting so intense, the pressure is so intense that this thermal radiation, this electromagnetic radiation, these X-rays, they just shoot out in these jets, and they call these the jets right over here. And these jets are light years wide, right? We're talking about thousands of light years going this way and that way. So again, it's just like all that pressure in a bottle with carbon dioxide, let's say, and it just the cork pops out when you're thinking about champagne, for example. Well, this is much, much, much more than that. And the gas, again, it hasn't reached the event horizon yet. Some of it is, so the gas will shoot out, and the other gas will be eaten by the black hole because it crossed the event horizon. And over time, millions of years, the quasar will die because the black hole just swallowed it. But again, the quasar is just a black hole that's feeding. That's the difference between quasar and black hole. And remember, our black hole in our solar system, well, not in our solar system, but in our galaxy, our black hole is Sagittarius A, which probably was a quasar billions of years ago. And again, the closest quasars we see are billions of light years away. And they're probably not quasars anymore because, again, quasars don't last that long when we're talking about the content of stellar star life. All right, that's our video.